afternoon, everyone. And thank you, Data Science Connect, Amelia, and Neo4j for the opportunity to speak here. So today I'm going to talk about contextual and semantic information retrieval. I'm Phani Dathar. I'm a Director of Graph Data Science at Neo4j. And specifically, I'm going to talk to you today about using knowledge graph to ground LLM responses. What does it mean? And I hope I'll convince you by end of this talk in like next 15 minutes that knowledge graphs are the amazing data structures that you would be looking at when thinking about large language models. LLMs are amazing, right? In my role 2 months ago, every other conversation included generative AI, and nowadays every conversation is about generative AI. So, and superior natural language understanding of LLMs, you've been hearing about this since today morning, even before coming here. All the great things that you can do, but still there are these challenges. There are these things that are barriers for adoption, personally as well as enterprise-wide adoption. And there are many things that are familiar to, I believe, most of you, almost all of you. But I'm going to point out two specific topics: reasonable answers, but not always accurate, and lack of enterprise domain knowledge, right? So those are the two topics I want to focus on. And because LLMs are inherently probabilistic models, they are really good at giving you reasonable answers, but the answers are not always factual because they don't know. They are only exposed to the data that they are familiar with, and they are not exposed to your domain or your organizational specific data. So how do we deal with that? And we still, all of us agree that this is a great opportunity. We all want to use it. We all definitely want to use it. But then because of these barriers for adoption, it is not there yet. I mean, there are no applications in production yet. It is still in the phase of lots of POCs going on, lots of different tests, different initiatives, but nothing concrete yet. So it is becoming increasingly common. If you look at various blog posts, various discussions that you're part of, it is becoming increasingly common that you need an additional data store. LLMs alone cannot give you a solution. You need an additional data store for grounding the responses or providing your factual information. Because if you look at enterprise data is both unstructured and structured data, right? Unstructured data is where we had lots of problems with, and we go to great lengths to capture data, break it down, extract facts from unstructured data, store it in a structured format, again, running analytics and so on and so forth. And in unstructured data, we have been struggling with different NLP pipelines until like December, and suddenly, it has become really easy to embed not only the sentences but paragraphs to documents into vectors, and then finding similar meaning text has become pretty easy or pretty powerful, right? But structured data still remains. And structured data, 98% of all the structured data are facts, and 2% are around dimensions. But those facts are really important for all the enterprises and businesses, and we rely on that data. So how do we take advantage of LLMs as well as not to lose on getting the real data from your enterprise databases? So here comes knowledge graphs. And if you look at other types of data structures like SQL and NoSQL and knowledge graphs and graph data structures, all of them are really great in providing the context that are required to ground large language models. However, if you really want to go beyond a simple understanding of what that particular entity means, but also how that particular entity is connected to its neighborhood, how is it related to your business overall, then you need a data structure that goes beyond storing data in rows and columns or in the form of a document. You need something like a graph data structure that can span across different data silos, that gives a unified picture of your data, and that you can cross from one part of the data structure to the other part of the data structure pretty easily and retrieve those patterns. And that's where graph graph databases come into picture. And knowledge graphs are a type of graph that has additional information in it. So graph data structures connect data from different silos, and the relationships between different entities and different silos become explicit in a graph. And in a knowledge graph, besides that factual data, you have taxonomies and ontologies that relate to the domain-specific knowledge and the semantics between different entities that describe your business. And once you have that rich connected data, then you have the necessary context that makes the whole response from an LLM more contextual to your business. And on top of that, knowledge graphs also allow you to enrich the context by adding more information. How do you add more information? Sometimes the relationships in your data is much more important than the data itself. And when you can derive insights from those relationships, then knowledge graphs can be used to capture that additional context as well. The more you make data contextual to your business, the more relevant these answers will be for your whatever downstream applications are. So today, we are going to go through these three phases: connect, enrich, and consume. And the third part of consumption is where LLMs come into picture. We still want to take advantage of the superior natural language understanding capabilities of large language models, superior text summarization capabilities of large language models, but we don't want to compromise on the data that's relevant to our businesses. That's why we need a combination of these two powerful technologies. So for those who are not familiar with knowledge graphs or graphs in general, what can you do with a knowledge graph? I'll take an example. Remember collaborative filtering and generating recommendations by looking at preferences? Let's say there is this customer, Jane, and you want to find recommendations for Jane. If you are using some kind of matrix factorization methods, you look at all the users of your business, their purchases, their preferences, and then boil down to a user matrix, a low-rank matrix for a user, trying to find similar users for Jane, and then trying to find recommendations for Jane. So now the curse of dimensionality comes into picture, the recommendations are still not personalized, and so on and so forth. On a knowledge graph, it becomes a simple graph pattern match. You start from the customer, you start from Jane, and then probe the local neighborhood, find similar users to Jane, and then start recommending products to Jane. So the whole thinking about how do you personalize or how do you do recommendations, how do you generate insights, it changes on a knowledge graph. And sometimes it is as simple as traversing 4 relationships. Like my colleague was saying today, you have trillion relationship graph, but you don't need to cross more than 1 relationship. That was amazing, right? So you have terabyte of data. Yes, but for insight for Jane, like I said, you probably don't need to go beyond 1 hop from Jane and then go find similar users and start finding the products. So knowledge graph is an amazing data structure that makes these relationships explicit, and then you can generate those insights pretty easily. Now the part where I talked about enriching the knowledge graph is, okay, now knowledge graph captures the data, the factual data, and the relationships between data. And we can also enrich the graph by adding more relationships. And what are these more relationships? Those are the derived relationships from the natural relationships. Like if you say, hey, there are 2 people who have made similar purchases in subsequent store visits, then there is some commonality between 2 people. By running a pattern match on a graph, you can create a new derived relationship. And then when you want to consume and ask the question, I want to find a customer that is similar to this customer, then all you need to do is go traverse this derived relationship and then grab the other one. So this additional context that you generate is what we call enrichment. And this enrichment can be done in multiple ways. One, by running graph queries, which are simple pattern matches. Or you can go a little bit advanced and run graph algorithms like community detection or clustering or anything that has to do with relationships and algorithms that work on relationships. Or you can reduce the dimensionality, generate an embedding representation of nodes in the graph, and then run unsupervised approaches like clustering or or some other downstream insights, like a previous speaker has shown a list of things that you can do with embeddings. And so for some more examples of insights from graph algorithms, again, these insights are coming from the graph algorithms, and then you can add them back to the graph, which will enable better context, more information from your data. For example, if I want to do what-if analysis on the graph, then I can run algorithms on a graph and then change the scores of a certain nodes in a graph. And then when I start asking questions about which data center is prone to cybercrime activity, then I can just go and probe the graph, pick up the nodes with a higher centrality score, and then use that as a response to the user. Because if I'm a cybersecurity analyst looking at my knowledge graph, I will not be interested in some generic information from an LLM, but I would be interested in getting the information from the graph, not only based on the factual data, but from the derived data. So you see the insights from these graph algorithms enhance the context, enrich the context in the knowledge graph, and this knowledge graph as a data structure captures the additional knowledge as well. So by using the graph, again, by using the graph, you're making use of the relationships. You're taking advantage of the relationships. By enriching the graph, you're taking advantage of the insights that come from your data. And all of this, we are building towards consumption at a later point. And we can also use LLMs for enrichment, like the previous speaker was also showing, and some of the speakers were showing. You can take the embeddings. They can either come from LLMs or bring your own embeddings from some Hugging Face models. And you can bring them to the graph and then store them as node properties. And this is one of a common use case where you have a bunch of text lying around, like PDFs. You take those PDFs, create chunks of text, and those chunks of text are converted into vectors, and those vectors are stored as, those chunks are stored as nodes in a graph, and the vectors that correspond to those chunks of text are also stored as node properties. Now you can take this graph and then use a native vector indexing in databases like Neo4j, and then you can run semantic search on your graph. So the semantic search is running on the graph, provides the local information that's domain specific, organization specific, and then you can use in summarizing your answers. And one more thing is you can even generate a richer representation. So in this representation, these embeddings capture the semantic meaning of chunks of text. In this representation, which are node embeddings are vector representations of nodes in a graph that capture the topology around that node, the structure around that node. Node embeddings or graph embeddings capture the topology, and when you combine the node properties, which are the semantic information, then these graph embeddings are even richer. They combine both contextual and semantic information in a single vector. Now if you do matching on those vectors, now if you index those vectors and start searching for similar vectors, the information that you get out of a knowledge graph is going to be contextual as well as semantic. And when you finally look at the results and then look at the, and then also take advantage of the graph traversals, then you get much more relevant, accurate, and contextual answers when you combine a knowledge graph with your LLM. So now, step number one is a knowledge graph where you build the graph with relationships. 2, you can enrich the graph in these few different ways. And then once you have that, then comes this consumption patterns. Now, this is where my topic for today is semantic and contextual information retrieval. Information retrieval from the knowledge graph, which includes both semantics as well as the context. And here is a simple pattern that shows how do you retrieve knowledge from Neo4j. Neo4j is a graph database, and today I'm specifically talking about knowledge graphs that are built using label property graph technology in a database, Neo4j. Right? So the flexibility of storing data in form of nodes and relationships, as well as properties on nodes, properties on relationships, different types of properties on nodes and relationships are available in Neo4j, and the knowledge graph that I'm talking about is built on Neo4j. So it's in this simple picture, you see that there is an application, user-facing application. User asks a question that is sent to an embedding model. It could be LLM. Generates. I mean, the embedding comes from the same. The embedding is from the same distribution as the embeddings that you generated for your text documents. And you get the implicit results, which are semantically similar based on vector matching. And then you can combine that with explicit results in relationships and derived relationships in your knowledge graph. And then you can take those results and then again combine them to put them together, ask LLM for summarizing the results, and then you can send it back to the applications. This is one pattern. And similarly, there is a different pattern where you want to take the, you're going to ask the LLM to generate cipher code so that you can run the cipher code on Neo4j database to extract results directly from Neo4j and then ask for generating an answer. So we have a framework that you can use and then integrate large language models with Neo4j database by using LangChain framework and using this graph cipher QA chain to get the context, which is the graph schema that you attach to your prompt, along with the training sample, a bunch of cipher queries, and then the question, and give it to LLM so that you can generate a cipher that corresponds to the schema that you provided as the context, so that you're not hallucinating there, or you're not creating new variables, new schema elements, and so on and so forth. And then you can also use fine-tuning, where you can have a bunch of examples, fine-tune a model, etc. But you can set up this framework pretty quickly and easily, and you can test this knowledge retrieval example with Neo4j. There are a couple blog posts that we have that we can share, which shows you this pattern of retrieval augmented generation using Neo4j knowledge graph as a source for contextual data. And this example is something that I really like. By the way, this is the retrieval augmented generation pattern with Neo4j. Here you see the Neo4j as a database, provides you the context that you need. And Neo4j, like I said, is used to build that knowledge graph that I talked about. And this knowledge graph will give you all the good things that I talked about for relevance, context, and then accurate or factual data. So, as an example, if you ask an LLM about this Hurricane Calvin, which passed Hawaii in July, when we were working on this, what is the impact of Hurricane Calvin? Then obviously, if you ask an LLM, you get Hurricane Calvin is caused by some flooding. It just flew south of Hawaii and so on and so forth. But if you want to refine this question and say who's asking, right? If an insurance company analyst is asking this question, then okay, it may be okay to give him an answer that Calvin just passed Hawaii. But what's more important is there are 50 policy holders in that region that are at the risk of that property loss, and that's what the impact of Hurricane Calvin. So how do you get that context, and how do you make a determination that this is what this particular analyst would need, right? So there are these different patterns that I talked about that can be used for fine-tuning and developing relevant cipher, generating insights, etc., and then orchestrating this whole process to achieve what we are after: semantic and contextual information retrieval. So just to summarize, if you start with your data, unstructured data, then you can get the first step done pretty easily. And then there are many tools out there where you just take those unstructured data, do some experimentation. How do you chunk it, generate vectors, put them in any vector database, and then you get the similar documents and content for user queries. Awesome. That works for some applications. But then once you start combining your structured data, then you want to go beyond the first set of results and then start capturing other information. So if you look at topics like pre-filtering, post-filtering, meta-filtering, etc., that is something that becoming increasingly common. Many tools are building, functionality around it, but graphs, knowledge graphs, already has that built in. So if you want to add context, all you simply need to do is take advantage of graph traversals, pattern matching. So after you find similar documents, you find connected things immediately within 1 or 2 or 3 hops out, and then get it to consume directly or give it to LLM for refined answers. And finally, once you start including graph algorithms and graph neural networks and all graph machine learning that's available in Neo4j, then you can further improve search relevance and insights by enriching your knowledge graph with the insights that you get from your existing data. So that's what I wanted to show you today, and I hope it has enough content to make you interested that knowledge graphs are providing you that extra information that you need compared to the other data stores. So, thank you. Okay, yes. So Neo4j is a database, and vector indexing is a functionality is a feature of Neo4j. So if you are asking, do I need both vector databases and Neo4j? No, you don't need. You can take the vectors index in Neo4j. Embedding algorithms, node embedding algorithms are included in Neo4j graph data science library that you can directly run on Neo4j graphs. Thank you. Oh, yes. So, first of all, understanding the user intent is the first part. Once you understand the user intent, then the corresponding cipher query is generated by this large language model. To help large language model generate the right kind of cipher query, you give some few short examples in the context. That's how you could generate the cipher query to extract results. It is still we are still working on it. We are still trying to understand the best way to contain the results or the cipher queries that run, but it is proving to be pretty powerful. So have we experimented embedding cipher queries itself? No, we haven't, because embedding cipher queries is not gonna give you that much advantage, I guess. But embedding graphlets and using the embedding vector, finding, like when a user asks a question, instead of finding a node that's similar to the user query, if we can find a neighborhood that's similar to the graph user query, then that provides you a better context for grounded response. So we are experimenting with that. Yes. Right. Yes. So so there are two parts to that question. So the question is, how do you verify the accuracy of the answer? So the first part is like when the cipher is generated and the cipher query is run on a database, whatever the result that comes out of the database is going to be factual, because the data that you put in Neo4j is the fact data. But then the question is whether the answer is complete. So the first is accurate, yes, but complete, That's where we need to figure out, like, we need to experiment with fine tuning, and then we need to experiment with, the extent of coverage these cipher queries provide. So there are a few metrics that we are trying. One is comparing the responses. Like, what kind of examples would train an LLM to give a better response, so that you are not missing out on some things like, for example, there is a patient journey database when we were looking at a question like, how many patients that are 30 years or older that are diagnosed with diabetes, and what happened to them 90 days after the first diagnosis. So now if you start thinking about it, the cipher query is pretty complicated because now you need to do a couple filters and then a path matching and so on and so forth. So what kind of examples would you require so that would you need to send to the LLM as part of your prompt augmentation to get such certain questions? It's something that we're still working on. But that's actually working on with different customers and prospects because they are schema dependent and the analytics and question dependent. Sorry. How much time do I have? I think I'm sorry. 3:15? Okay. All right. Cool. All right. Thank you. Yes. Yeah. Yes. You have a question?
So in one of the slides that you showed, you were basically combining the prompt method from Google and the text from the Retrieval.
Yes.
So that combination is that
Yeah.
and go to and it's combining prompt text and level.
Yeah.
Is it simply like adding two different vectors, one coming from the Retrieval?
No, prompt is the English language prompt, right? So sorry, the prompt includes context and relevance, meaning the prompt is just the question that posed by the user, and then the graph schema that comes from this graph cipher QA chain, and then the examples that we added to the prompt, and then some other directions to the LLM what to generate. So the prompt is a package that goes to the point number 2. But what happens is, you see the prompt when it goes to LLM, generates cipher, and then Neo4j generates results, and the question will be combined with these results set and then sent to LLM. Okay? So there are two different paths there. One path is generating cipher, the other part is question, and then the answer set, and then asking for summarization. Okay, sure. Thank you.